Okay, so let's talk about the power reducing identities. Now, the good thing is that what we're about to see and learn isn't new. It's really using what we already know. So it says here, what can I do to reduce a power? What identities that we've already used have two different powers in the equation? So for example, and this is kind of what it's getting at, think about if I had sine squared of theta, how can I rewrite it so that there's no more squared term in it? And if you're thinking about, well, sine of theta times sine of theta, that's not what I'm looking for here. So think about this and then let's talk. So think, think, think. Put me on pause if you have to. Okay, so immediately when I think of this, I think back to our double angle identity for cosine of 2 theta. Remember, we knew that cosine of 2 theta is 2 cosine squared of theta minus 1, and it's also 1 minus 2 sine of squared of theta. 1 minus 2 sine squared of theta. So if I solve this for cosine squared of theta, I get cosine squared of theta is 1 plus cosine 2 theta over 2. If I solve for sine squared of theta, I get 1 minus cosine 2 theta all over 2. Okay, so these are the two identities we would want to know. For tangent squared of theta is just a little bit different. I know tangent squared of theta is sine squared of theta over cosine squared of theta, which if I simplify both of these based off of what I wrote up here, that's just 1 minus cosine of 2 theta all over 1 plus cosine of 2 theta. Okay, like I said, the main thing that we want to keep in mind is like these aren't new. This is just rewriting this equation and solving for something else. So just keep that in mind. This is reducing a power. So going from a squared term to not having a squared term. So make sure that we understand how we can use the power reducing identities and how they're derived.